Hello, Calculus 12 students. Mr. Yoon here with another video lesson for Calculus 12. And in this video, I will be covering the fundamental theorem of calculus. And basically, the fundamental theorem of calculus is a method in determining the exact area under a curve. Now, in our previous lessons, we have an idea of how to approximate the area of the curve. And we did this by drawing rectangles or trapezoids underneath the curve, and this is a very good way to approximate the area. So let me kind of start off this lesson by kind of reviewing some of the terms that we kind of talked about in the last lesson. So if I kind of zoom in on this diagram here, and you'll notice that I have this curve here in yellow, and if I wanted to kind of approximate the area of the curve, I could go ahead and draw some rectangles. Now, in this case, I'll have n equals to 6, meaning that I have 6 rectangles, 1, 2, 3, 4, 5, and 6. So if I'm talking about maybe this x value of 6 here, then the height of this rectangle is simply going to be f of x of 6. Okay, so where this 6 right here matches with that x value of 6. So that is the approximate height at that point. And then we also had the widths, so the width here. So if I go from 2 to 3, this would be the width. Okay, and you'll notice that the width for each rectangle is the same. Now, if you look at one x value and go to the next x value, this is really a change in x, going from 1 to 2. So since that's a change of x, sometimes another way to represent the width is called delta x, all right? Because the width is really a change of x. We're going from like the x value of 1 to the x value of 2, so we call that change of x, and that can also be denoted as delta x. Okay, so that's some of the things that we kind of looked at last class. Now if I zoom out here, I have 3 diagrams here, and notice that if I increase the number of rectangles from 6 to 12, the approximation for this curve right here, or sorry, this graph right here, the approximation under the graph is a little bit, it looks a little bit better than the graph when we have only 6 rectangles. And then if we go ahead and increase the number of rectangles to n equals to 30, if you compare this approximation, the area under the graph, and compare that to maybe like one of the previous approximations, I think everyone can agree that this approximation here when n equals to 30 is much better. So the general idea is if you want to improve your approximation of the area under the graph, what you can do is you can increase the number of rectangles. Okay, so if you increase the number of rectangles, the approximation slowly gets better and better and better. Okay, let me just delete all this here. Okay, so just to summarize again, if we increase the number of subintervals n, we can actually improve the approximation for the area. Now, if delta x is the width for each rectangle and f of x of k is the height for each different rectangle, then we can represent the area under the curve as, let me just kind of blow this up here. Another way that we can represent the area is by using this summation notation. So this right here, this delta x, that's kind of like the width right there. And this f of x of k, that's like the height for each different rectangle. And notice that I start at k equals to 1. So if k equals to 1, that means I'll start with an x subscript of 1 here. So if I went ahead and expanded this, this would be f of x of 1 times delta x. So that's the area of the first rectangle. Sorry here, and then plus, and if I increase the value k, this would be f of x of 2 times delta x, and then I'd keep on going. Now, I don't know what the value of n is, but if the value of n here was 6, then I would keep on going, and I would stop at f of x of 6 times delta x. So this expression right here would be the last rectangle in your diagram. And if I go back to the original notes here, if I kind of delete all this here, just 1 second, delete all that. That would pretty much represent this rectangle right here, the last rectangle there. So this guy right here represents the last rectangle in your diagram here. Okay, so hopefully that notation makes sense. We're just summing up all the rectangles. Now, if we increase the number of rectangles, Just one second here, let me just change colors here. So if we increase the number of subintervals to the number of rectangles, then we can actually improve the approximation, and eventually if we increase the number of rectangles to an infinite amount, then we can get the exact area under the curve. So the exact area under the curve is represented by this notation right here, which is the same notation as above. But what we're saying now is we want this n value to be very big. Okay, we want that very big. We want an infinite number of rectangles, and one way to represent that is we can use this limit notation right here, meaning that we want n to be very, very big so that we have an infinite number of rectangles. And if we have an infinite number of rectangles, the approximation is so good that it's pretty much the exact area under the curve. Okay, so this is the first formal definition that we're going to use for today's lesson here. The area under the curve can be represented as the sum of all the rectangles from k equals to 1 to an infinite number of rectangles. And another way of kind of representing that using like integrals and antiderivative notation is by using this integral sign of f of x dx equals to f of b minus f of a. And throughout this lesson, I'm going to try my best to kind of describe what this red box, the notation that red box, what that represents. Okay, before I kind of break this down into like its meaning, this dx right here, once again, if you see a dx, that's the same thing as the width of each rectangle. This f of x means the height of each rectangle. And this a point is kind of like what we call your lower bound, like where you would start. And this b right here is called the upper bound. And that's where you will finish. Okay, and this notation right here, I'll explain this once again, a little bit more in detail on the next slide here, but that's really the antiderivative at b minus the antiderivative at a for that function. Okay, so right now this the notation here is kind of all over the place, but please give me a few minutes to kind of explain what the notation means. Okay, so let's move on here. Okay, so the fundamental theorem of calculus, what that is saying is that the integral from a to b of f of x dx is going to be capital F of b minus capital F of a, where f is the antiderivative of f of x. Okay, so let's go ahead and just kind of give you a visual diagram of what this part means right here. And if this is your lower bound, that means I'm talking about this value of a right here. And if this b right here, if that's called your upper bound, that means I would be stopping at that point right there. So this right here represents, this notation right here represents the area between a and b. Alright, so if I drew like a random sketch here, if I draw a random sketch right here, it just represents the area under the curve between a and b. Okay, so let's go ahead and just summarize that one more time. So if this is your integral from a to b of f of x dx, this notation right here just represents the area under the curve. And a is going to be your lower bound, and b is going to be your upper bound. Okay, and in order to kind of so visually I think this is not too bad to kind of understand the notation here, but later on the definition breaks down as this being the antiderivative of f of b minus the antiderivative of capital A. And this right here is the antiderivative. Okay. And that is the fundamental theorem of calculus. Okay, so that's the notation that's being used to represent the fundamental theorem of calculus. And now what I'm going to do next is I'm going to walk you through a numerical example, and then I'm also going to kind of explain why the antiderivative is connected to the area under the curve. Okay, so before I get into explaining why the antiderivative is connected to the area under the curve, let me go ahead and just do a very simple example so that we can understand what this notation right here means. Okay, this capital F of b minus capital F of a. Okay, so let's just kind of walk through a very simple example here, and let me just blow this up again. So the question here is, I want to find the area under the graph of f of x equals to x squared from x equals to 1 to x equals to 2. Okay, so this x equals to 1, this is kind of like your lower bound. So this means a equals to 1, and this x equals to 2, that's your upper bound, so that means b equals to 2. Okay, so I'm focusing on the value of 1 and 2, and basically I want to find the area under the graph between x equals to 1 and x equals to 2. Okay, so if you read the problem, and if you want to visually kind of draw what you're kind of looking for the problem, it will look like this red, well, it's not really a trapezoid, but it looks very similar to a trapezoid. Okay, so we want to find that area. Now, if I want to set this up as an integral here, this would be from a to b of f of x times dx. And let me just go ahead and expand the definition here. This is f of b minus f of a. All right, so if I went ahead and plugged in the numbers here, this would be the integral from 1 to 2 of f of x. Now, what is f of x? Well, f of x is just x squared, so this is going to be x squared times dx. Okay, so this means the area under the curve of the function x squared from 1 to 2. All right, so this notation right here means that I need to go ahead and find the antiderivative. Capital F means the antiderivative of f of x. Okay, so let's go ahead now and find the antiderivative of this expression here in the green box. If I go ahead and find the antiderivative, that's going to be x to the power 3 divided by 3. Now, in our previous lessons, I always told students to add a c here, but we're not going to add a c this time because we know that we're working with the function x squared, okay? We're not working with x squared plus 4 or x squared minus 6. The graph that we're focusing on is x squared, so we don't need to add this extra c because we actually know the kind of graph that we're working with, okay? Now, the notation that's used for calculus is that once this expression right here is the antiderivative, right? That circle is the antiderivative. But we also need to include these the upper bound and lower bound. So the notation that's kind of used after this is that we draw a straight vertical line, and I would put a lower bound 1 here and an upper bound 2 there. So this expression right here means I want to find the antiderivative. Sorry, the antiderivative is x cubed over 3, and I need to evaluate that between x equals to 1 and x equals to 2. Okay, so that's what this notation means. It's very similar to, if I say find d of dx of x squared at x equals to maybe 4 here, is very similar to this notation that we saw way back in chapter number 3, where I'm asking what is the derivative of x squared at the value of x equals to 4. And that's why we have this kind of vertical line here, because we want to evaluate it at a very specific point. Okay, so if I went ahead and used this definition here, f of b minus f of a, well, this is the value of b and this is the value of a. So all we do now is we insert the value of b and a into the antiderivative, which is x cubed over 3. So if I went ahead and inserted the numbers here, this would be a bracket here. This would be 2 to the power 3 divided by 3 minus 1 to the power 3 divided by 3. Okay, so if I just kind of match this up here now, let me just erase all this now. So this part right here would represent that part right there, and this part right here would represent that part here, and that minus sign is that part right there. And if I went ahead and evaluated this, this would be 7 divided by 3, which is roughly 2.3333 repeating. Okay, so let me go ahead now and just show you that this is indeed the actual area underneath our graph. So what I'm going to do is I'm going to bust out my graphing calculator here. I'm going to turn it on, and if I go to y equals, if I plug in y equals to x squared, if I graph it, there's my graph right there, y equals to x squared. And if I hit second and trace, and if I go down to option number 7 here and hit enter, it's asking for a lower limit. So that lower limit is x equals to 1, and my upper limit, which is my b value, that's going to be 2. If I hit enter, there you go. The graphing calculator will actually calculate the exact area in the graph, and this answer of 2.33 is very similar to the answer given by the graphing calculator. Okay, so that example right there kind of illustrates the notation that's being used for the fundamental theorem of calculus. So from now on, if you see this kind of a notation here, all this stuff in yellow, I hope that you understand how it's being applied to a problem where you're finding the area under the curve. Okay, so I've taken some time there to explain the notation that's being used. What I want to do next is I actually want to explain to you guys why the antiderivative is connected to the area under the graph. Okay, so let me just kind of blow this up again, zoom in here. So I want to go over, the next part of this video is I want to go over some examples where we're trying to understand why the integral is f of b minus f of a. Okay, so in order to kind of show you why the antiderivative, which is this f of b and this f of a, in order to show you why the antiderivative is connected to the area under the curve, we're going to start off with a very simple example, and we're going to graph f of x equals to 2. And then we'll go ahead and graph its area function as well. Okay, so if I focus on graphing f of x equals to 2, that's just a straight horizontal line, right? This is not tricky at all. I'm just graphing f of x equals to 2, and one of the reasons why I'm starting off with this example is because this example is very easy to calculate the area in the graph, and therefore it's going to be very easy to show you how the antiderivative is being derived from the area under the graph. Okay, so this is f of x equals to 2. All right, that's not hard there. Now, if I ask you, let me just ask you some general questions here. If x equals to 1, the area under the curve is, okay, so if x equals to 1, which is right here, what is the area under the curve from I guess from x equals to 0 to x equals to 1? So if x equals to 1, let's ask ourselves, what is this area under the curve? Okay, so if x equals to 1, the area in the curve is going to be that rectangle, which is going to be a width of 1 and a height of 2, so the area is going to be 2. Okay, now let's kind of change this up a bit, and I'll ask you if, let me just delete this now, if x equals to 2, then what is, sorry, let me just go back here, I apologize for all this. When x equals to 1, the area in the curve is 2. Now if I repeat the same question, if x equals to 2 now, what is the area under the curve? Okay, well, if x equals to 2, let's go ahead and just find the area now. The area here now is going to be 2 times 2, which is going to be 4. Okay, now if x equals to now 3, what is the area under the curve? Well, if x equals to 3 now, the area under the curve is going to be 3 times 2, which is going to be 6. Okay, so basically if you do draw this horizontal line there, f of x equals to 2, it's pretty easy to calculate the area for certain x values. Now what I'm going to do next is I'm going to go ahead and graph the area as a function of x. So if I go ahead and graph the area now as a function of x, let me just draw a little table of values here. What are the x values that I'm using for this example? Well, I'm using the x values of 1, 2, and 3. Okay, so my x values are 1, 2, and 3. And what is my area as a function of x? Because I want to graph that. Well, when x equals to 1, my area here is 2. And when my x value here is 4, when my x value here is 2, then my area would be 4. And when my x value is 3, then my area here is 6. Okay, so let's go ahead now and zoom out so we can get all this together here. Okay, let's go ahead now and let's just graph the table of values right here. Let me just erase all this so that we have a little bit of room here. Okay, let's take a look here. So when x equals to 1, I have an area of x of 2. So if this is my x value and this is area of x, a of x, so when x equals to 1, I have a value of 2, and when x equals to 2, I have a y value of 4, and when x equals to 3, I have a value of 6. Now if you go ahead and connect the dots here, the equation of this graph here in yellow right here, the equation of that has a slope of 2, so the equation here is going to be y equals to 2x. Alright, so this is the equation of that yellow graph. Now ask yourself, what is the relationship between this graph, which is essentially y equals to 2, what's the relationship between this graph, y equals to 2, and this graph over here? Well, this 2x is the antiderivative of the original function, which is y equals to 2, right? So if you have y equals to 2 here, what is the antiderivative? What is the antiderivative of 2? Well, that is 2x. All right, so the area under the curve, guys, the area under the curve right here is actually related to the antiderivative. Okay, and let me show you that one more time with another simple example. I'm going to my next kind of example to kind of show you how the antiderivative is connected to the area in the curve. Let's go ahead and graph f of x equals to 2x, and then we'll graph its area as a function of x. Well, if I want to graph y equals to 2x right here, I mean, that has a slope of 2, so we're going to be going up like this, 2 and 4, and 3 and 6. All right, so let's go ahead and connect the dots here. There is my there's my linear shape right there. And let me ask you a few questions again. If x equals to 1, that's this guy right here, what is the area? What is the area under the curve? Well, if x equals to 1, I go straight up and I get this triangle right here, right? What's that area? Well, the area of a triangle is base times height divided by 2. So 1 times 2 divided by 2, the area is going to be 1. Okay. Now, if x equals to 2, the area is going to be what? Well, if x equals to 2 now, we need to calculate this area now in red, a bigger triangle. What is that area? So the area of a triangle is still the same. It's base times height, which is 2 times 4 divided by 2, and that area is going to be 4. Okay. And now if x equals to 3, what is the area under the curve? Okay, when x equals to 3 here, the area under the curve is going to be 3 times 6 divided by 2, which is going to be 9. Okay. Now let's go ahead and graph the area as a function of x. So if I want to go ahead and graph its area now as a function of x, my table of values would be x and a of x. My x values are again 1, 2, and 3. So if this is 1, 2, and 3, those correspond to my x values right here, 1, 2, and 3. And my areas would now be, sorry, let me just delete that. This is going to be 1, this is going to be 4, and this is going to be 9. And these corresponding values here in blue, those pretty much represent the areas. Now, if I go ahead and graph this, this is going to be 1, 1, 2, 4, and 3, 6 up here about 9. So if I went ahead and graph this to the best of my abilities here, this would represent a parabola. This is actually the parabola y equals to x squared. Okay, and the original graph was y equals to 2x. Now once again, ask yourself, what is the relationship between the original graph y equals to 2x and its area under the curve as a function of x? Well, if I have y equals to 2x, then its antiderivative must be x squared. Okay, so there it is. Based on those examples there, hopefully I've shown you that the area under the curve is actually, the antiderivative is connected to the area under the curve. Okay. All right, so that's why we've been talking a lot about the antiderivative, because once we know how to find the antiderivative, we are able to find the area under the curve. Okay, so now let's kind of summarize the notation for this fundamental theorem in calculus right here. So the area under the curve f of x is given by another function which is always the antiderivative of the given function, all right? And that pretty much summarizes this relationship right here. Okay, great. Now let's go ahead and kind of talk about the notation a little bit more here. If I have this expression right here, this integral from 0 to b of f of x dx, once again, if this is f of x, that represents this graph right here, and this dx right here, that's pretty much the width if you have rectangles. And let's take a look at this upper limit b, which is right there, and let's look at this lower limit of 0, which is going to be over here. So if I wanted to go ahead and just kind of graph this, a simple sketch, that's going to be from here to 0. So it's going to be this green area underneath the curve. Okay, so that's how you would sketch this integral right here, that's being this whole integral in yellow right there. If I asked you to do a simple sketch, you would draw a graph like that. Now if I went over now and looked at this next integral right here, my lower limit is still 0, and my upper limit here is a. which is right there. So if I asked you to kind of sketch this, then your sketch will look like this. I'll put this in blue now, like that. Okay. Now let me kind of connect these two integrals to the actual notation that's being used for the fundamental theorem calculus. Pretty much, if I ask you to look at this now and graph that, notice that this is your lower bound, which is right here, and this is your upper bound, which is right there. So I want to find the area between A and B. Now if I want to find this area right here in yellow, what you're doing is, let me just zoom out here. Let me, sorry, where's the zoom button? View, zoom out. So once again, if you want to find this area right here that I'm kind of like now highlighting here in red here, what you're going to do is you want to take the area from 0 to B. And if you subtract this area right there, then you would get that area right there. And that's why you have this minus sign right there. All right, so if you're wondering why we have that minus sign, it's because we first evaluate the area of f of b. F of b is pretty much this blue area, this blue area that I'm highlighting right here. That's f of b, this blue area. And if I go ahead and subtract this purple area, which is that right there, blue minus purple, if I minus that purple area, then I'm left with this, this final area here in green. Okay, so that's why the notation is set up like that, and hopefully you can see what the notation means by these visual aids right here. Okay, all right, so that is basically the theory for the fundamental theorem of calculus, and in the next part of the lesson I just go over some numerical examples, and then we're pretty much finished. Okay, so for a question like this is a very common question that does get asked in this course here. So what I'm going to do is let's go ahead and walk through a simple example here. So once again, if you see this integral sign, that means we need to take the antiderivative. Notice I have all x's here, so this dx here does match the notation for antiderivatives. But now that we have these boundary points, let's go ahead and evaluate what this integral will be. All right, so let's find the antiderivative here. So this is going to be 6 times x to the power of 3 divided by 3. Remember, we take the exponent, we add 1, and we divide by the new exponent. Minus 6 times x to the power 2 over 2 plus 4x. Now, I don't have to include c. Do not include c because we're trying to find the area under the curve, right? We're trying to find the area under the curve between -2 and 3, right? So we know the exact function we're working with, so we don't need c anymore. Instead, what I'm going to do now is, since I've taken the antiderivative, I'm just going to draw a straight vertical line because I want to evaluate the area under the graph between -2 and 3. Okay. And if you want, you can go ahead and kind of simplify, this expression right here before actually plugging the numbers. This is the same thing as 2x cubed, and this part right here will be 3x squared. All right, so let's go ahead now and evaluate this. This does take quite a bit of time here because we need to evaluate this upper bound, and then we need to minus that from the lower bound. So let's go ahead and plug the numbers in now. This is 2 times 3 cubed minus 3 times 3 squared plus 4 times 3. All right, so now I'm done with all my 3's, right? I've inserted all my 3's into my antiderivative, and then I need the minus sign, right? Because the integral from a to b of f of x dx is the antiderivative of your upper bound minus your antiderivative of your lower bound. All right, so I need a minus sign there, and then I'll put a bracket here, and then I'll evaluate my lower limit here. So this is going to be 2 times -2 cubed minus 3 times -2 cubed plus 4 times -2, all in brackets. Okay, so I'm going to pause the video and get right to the final answer here. So just give me a second while I pause the video, and then I'll unpause and give the final answer here. Okay, so I just finished unpausing the video here, and after you go ahead and calculate all the numbers and insert all your numbers and simplify, you get an answer of 75. All right, and we'll just call that 75 units. Okay, and you can also just kind of verify this using a calculator here. If you bring out your graphing calculator here, you can type in the original function into your calculator. You can go ahead and graph it. You get something like that, and if you want to go ahead and now calculate the area between -2 and 3, hit second and trace, go down to option number 7. Sorry. And then if you hit option number 7, it's asking for a lower limit, which is -2, and your upper limit should be 3. And if I go ahead and calculate using the calculator here, notice that my area here will be 75. So 75 does indeed match the answer that I did get there. Okay. All right. Let's move on to another example. Now, actually, this next example right here, I probably won't do this. I would probably get you to try this on your own. The only kind of advice I have for this question is please rewrite this integral as 1 to 2 of 9x plus 12 plus 4x to the power of -2 dx. So if you go ahead and change that denominator into a power here, it's much easier to take the antiderivative. And you can go ahead and just check your answer using your graphing calculator, but go ahead and do the algebra on your own and just confirm that you can indeed get the same answer as your calculator. In fact, I'll just go ahead and do this in my calculator right here. Let's just hit the y equals, clear that, 9x plus 12 plus bracket 4 divided by x squared, I guess. Close the bracket, graph that. If you do that, there's your weird graph right there, and let's go ahead and calculate the interval, which is the area of the curve from 1 to 2, and you get 27.5. Okay, so 27.5 is your answer. So see if you can get 27.5 on your own, and feel free to use like a calculator to kind of simplify your calculations, whether it be a graphing calculator or a scientific calculator. Doesn't matter to me. Okay, let's move on to the final example here. Okay, so in this problem I have a fractional expression here, and for this example I'm going to give you a little hint here. There's a rule going back from our previous lesson here. There's a rule where the integral, if you have the integral of f of x divided by the antiderivative, or sorry, the derivative, this is going to be ln absolute value of f of x plus c. So this is one of the rules that we did talk about when we're dealing with fractions. And you'll notice that if my denominator here is x squared plus 1, is it possible to get the original function on the numerator? Absolutely. So if this is going to be, oh sorry, I screwed up the definition here. It's supposed to be f of x on the denominator, and the numerator is going to be f prime of x. But this that final result is still the same. So I do apologize for that little mistake here. If I look at my original function, which is f of x, let's go ahead and just put that in my denominator here. Now, what is the derivative of x squared plus 1? Well, that's going to be 2x. Okay. So notice that I still have a 4 here. So what I can do now is I can put my integral sign and put another 2 in front. If I put this 2 here, 2 times 2 is going to be 4x, which gives me the numerator right there. Okay, so I can rewrite the problem like that and put my dx here, and this is going from -1 to 3. All right. Now, whenever you have these boundaries, -3 and -1, we actually call that a definite integral because we can actually find the area under the curve. If you're not given the boundary points like 3 and -1, if you're not given that, we call that an indefinite integral. And when you have an indefinite integral, always include a constant c. Okay. But whenever we have the actual numbers here, 3 and -1, we don't have to include c because we want to find the exact area underneath the curve. Okay, so what is this antiderivative right there using this rule right here? Well, that's going to be ln of f of x, which is x squared plus 1, and that's being evaluated, sorry, I need a 2 in front, and this is being evaluated from -1 to 3. Okay. Now, if I go ahead and simplify this, this is going to be 2 times the ln of, well, first evaluate 3, so I plug in 3 into my x values here, so this is going to be 3 squared plus 1 minus ln of, now I need to evaluate my lower boundary, which is going to be -1 squared is going to be 1 plus 1, close the brackets, and this is everything here is being multiplied by 2. Okay. Now, if I went and expanded this, sorry, if I go ahead and simplify this, this is going to be the ln of 10. You know what? I know 10 is going to be positive, so I'm just going to drop the absolute value here. So that's going to be ln of 10. And the reason why I'm dropping the absolute value is because I know 10 is positive, so I don't need to have the absolute value there. And this is going to be the absolute value of 2, and then I'm going to close the bracket here. Okay. Now we can further simplify this, because using one of our log rules, if I have log a minus log b, that's the same thing as log a over b, and that also applies with the ln rules. So if I go ahead and use this logarithmic rule here, this is going to be 2 times ln of 10 divided by 2, which is 2 times ln 5. And there you go, there's your final answer right there. Okay, so that concludes this lesson video, and we'll see you guys later then.